Hi there. So we're moving on to something new now for the next couple of sessions. So far we've been building a web application. The technical term might be a server-rendered web application using Node. And we've been building it using the Happy framework, as you know, Handlebars templating library. And we've been experimenting with some repository-like patterns for having different databases slotted in as we meet certain demands or certain runtime requirements. This session, though, we're going to leave that in place and we're going to explore API development, and specifically how can we make available the services we've already built as an API rather than a traditional web interface. Now, before we get into that, I'm going to take a little detour back to test-driven development again, another case study. Purpose of these case studies is to give you a sense of what TDD is like, test-driven development, sense of the benefits of it, and what the practice might lead to. That is, try to get or climb into the mind of somebody who is using TDD for quite a long time and thinks about tests as much as they think about actually developing features. So this is a case study from a well-known source. Hopefully it gives you a sense of the practice. Second thing we're doing this morning or today is focusing on Mongo again and looking at relationships between Mongo objects or documents. So it's a little bit deeper into how we can have one object in a database referring to another, which is a very common pattern that we will use certainly in our playtime and in your assignment work. With that out of the way, then we can get into this new aspect I've been mentioning. We'll start by exploring what an API is and specifically what REST means. A REST style API is a very common pattern in the industry now. APIs allow features of applications to be exposed, not just as a simple web application, but to other programs. And we'll discuss that a little bit. Those other programs most obviously could be mobile, but they could be other server applications that are accessing your facilities, or they could be front-end applications that are using the API to reach into the back end, and we'll be spending a lot of time considering that particular use case. We'll then get on to exploring how to put together these, what we call endpoints. It's like API points or API services. It's kind of an interchangeable or slightly vague term. Happy is the framework we'll be using, and Happy, I guess, means happy programming. But the API in HAPI refers to the facilities that this framework we're using has for supporting API development. In fact, Happy is kind of an API first framework. So it's designed to make building APIs comfortable and expressive and reasonably powerful. There's not an awful lot to learn in Happy to do this because we're already exposing kind of APIs via our web routes, but now we're decoupling the handlebars infrastructure and we're exposing effectively our controllers we write for this purpose as our API endpoints. We'll explore that here. Particularly, we'll explore one or two tools for accessing endpoints, or testing them rather. And then we'll get on in our final topic here to explore explicitly testing endpoints using the test-driven development tools we have already started looking at, particularly Mocha and Chai, the test runners inside VS Code, and our ability to exercise the API and verify that it's behaving as expected. In other words, attempting to apply our test-driven principles to scaffold out our API in a robust manner. Again, test-driven development becomes quite important here in that if we can have secure APIs fully tested before we build any clients, say any mobile or any other applications, then we've got a fairly solid foundation to build on. If we don't have tests, then our API implementation, well, we're kind of going in hope rather than confidence. Okay, that's it for today. It's a useful session, I think. We're continuing with playtime, so we've got the same case study to push forward. This time, the existing web interface will be left intact, and we will be building a new API to reveal those facilities as endpoints. Okay, we'll get going then. Developing an application in test-driven mode takes a little bit of practice. I'm going to take another case study here from this fairly influential text on the field. And we're looking at developing something like a little video player application, or specifically an individual component. Point about this case study is just to give you a feel for thinking methodically about tests, perhaps building tests in advance of the feature you're implementing, and understanding the relationship between the evolution of the tests and how the features we're building progress in parallel. Essentially, how the tests guide or shape the direction of the implementation. So the application might be something simple like this. We've got a class video player, and this video player defines a range of functions which encapsulate what we're trying to build. Fast forward, rewind, get the current position, mark a position, so a named bookmark, maybe our chapter, and then go to that position is the idea. So these might be ultimately hooked up to buttons on a player or physical buttons on an implementation of a player, but we're just imagining it as a class. Our starting point might be to assemble a video player class to implement that interface. So we're laying out the skeleton of our implementation here. In the literature, this is sometimes called the system under test, or the SUT. I don't see that phrase used too often these days. So we're setting up some fields, some state if you like. We've got the overall duration of the media, the current position, and then we're kind of thinking forward here to the chapter or markers. We're imagining it as a map of marks. We also define our constructor to initialize the length of the media and then create our empty set of markers. And finally, we return the current position here as a field. So all of this we might do first without thinking too much really, but imagining this is our basic implementation. And note that there are no implementations at all of these various fields. We haven't thought about them and we haven't considered them. We might then start to theorize about the kind of tests we'd need, and might come up with maybe on a back of an envelope sort of computation. These tests: verify initial position is 0, fast forward by some amount, not past the end, then rewind, should be at the same initial location. So it's kind of a test to verify that our forward and back works. Rewind, not past the beginning, then go forward, we should be at the initial location. Go beyond the end of the tape and see what happens. We should be able to react appropriately to that and not go beyond the tape. We shouldn't have a marker that is out beyond what is initially defined as the duration. Do the same thing in the other duration. Mark various positions and return to them after moving the current positions. Mark a position and return to it without moving in between. So if we're thinking methodically, these are the kinds of things we start to articulate, either physically by noting them down, or it's just part of our methodical thinking as we're building the feature. You build a test fixture initially. We are using JavaScript, and we're going to be using the suite feature of Mocha. This is how you would do it in JUnit. You build a test class. Your fixture is the object you're going to be testing, system under test. And set up and tear down, and we have something exactly like this in our JavaScript tests are run before and after each test. So we're getting test isolation. We don't want the tests in any way to be interfering with each other. First test then, test beginning of tape. This test, all it does is checks to see if for a completely new editor, tape machine, whatever it's called, we're at position 0. So it's the very simplest, most trivial test. All it's testing really is that we constructed the object correctly. So what we've tested in that test here is exactly that this class here, the system under test, works as expected. So the next one, fast forward by some allowed amount, not past the end, then rewind by same amount. We should be at the initial location. So we are going to write the tests here. I'm going to set the tape to be 100, say, minutes long, let's say. Test fast forward is our test. So I'm going to go forward 30, back 30. I should be at 0. So in other words, I'm checking that my forward and backward motion is correct. Maybe I write that first, it fails, and then I put in the minimal logic you can see here, and then the test passes. So test failing first, then just enough to get the test to pass. Next one, rewind by some amount, not past the beginning, then forward, should be at the initial location. So it's the opposite of the other test, except we're going rewind. So you can see the basic logic here of the test. It seems straightforward enough, and the implementation here should pass. So we're starting to make some progress now. Keeping going then, let's try fast forward past the end of the tape, rewind by the same amount. I should be at the initial location by the appropriate amount to reflect that you can't go beyond the end of the tape, if you get my drift here. So I write the test now, fast forward. I've got fast forward implemented, I've got rewind implemented. So I'm going beyond the end of the tape, which shouldn't work. And in fact, this will fail initially. So my first implementation will not have worked, because my first implementation didn't really take into account the overall length of the media. In other words, I should be not going beyond the duration. I needed to re-implement the fast forward function, getting rid of the old implementation and replacing it with this version. So what we're doing here is one of the principles of test-driven development, which is the idea that you do the minimum to get your test to work, your basic test. And then as you develop more tests, you'll need to implement or revisit the minimum you've implemented to make it work more completely. So this is the same in the other direction, really. The rewind needs to take into account the fact that we can't go before the start of the tape, getting into negative numbers, which doesn't make sense. My last test then exercises the go-to mark and mark time position. So we're putting in markers based around a simple map of strings. So it's a fairly trivial example, really, but the takeaway is thinking methodically about the feature we're trying to implement, writing some tests before we've even implemented the feature, watching the tests fail so we know our test infrastructure is working okay, do the minimum to make the test pass, then develop more tests which perhaps stimulate some bugs in the system you've implemented because you didn't complete it. The test fails again. Fix those things that have failed. You're getting back to a passing state. And in this manner, you're gradually evolving or growing the system under test. You're evolving it to a complete state rather than going straight in coding for half an hour, and only when you're finished coding do you consider how it might work. If you hadn't been using tests at all, you'd have to scaffold up a user interface and start exercising it, which could be tedious, and you may miss a whole range of features. Using test harnesses and using the fixtures, we're able to verify the features incrementally as we build them, gradually growing our application such that it is converging on the set of features we had envisaged. When working with Mongo data stores and document stores in general, we have some options regarding relationships between objects, between documents, in this case, that weren't really on the horizon when we're working with SQL databases. So we'll take a look at some examples of that to see if we can make sense of it. In a relational model, relationships between entities evolve fairly naturally. This blog application here, we've got users, authors, author makes an entry is in the blog, we have tags and comments and so on. In a document version of such a thing, we may have quite a different configuration. Here we've got a user collection and we've got a blog collection. And inside the blog, we're storing or embedding within it our comments, tags, authors that are all part of an entry. In other words, the MongoDB model has evolved possibly 2 entities, if that's the equivalent, rather than 6, as we're showing in the example above. In other words, we can choose to embed objects to encapsulate the relationship, or we can use object references. So what does this mean? Well, if we're going for embedded data models, it's sometimes called denormalized because we're not separating them out into separate normalized relationships. Then we're envisaging the embedded object to be contained or encapsulated completely within the container, the contained object, if you like, or the owner. So our contact details are completely encapsulated within this enclosing user object in this instance. So one record, if you like, containing this encapsulation relationship. We might use them when we want efficiency in our read operations. So when I do a read from the database, I want to possibly pull back all I need in one read. So I'm getting the contained operation here without a separate fetch, similar with the update. However, we should be aware that if we're using embedding like this, the documents may tend to grow. And if we're continuing introducing new entities, new model objects, if you like, and always sticking with the embedded or contains relationship, our data stores might yield very large documents and thus eliminating possible some efficiency advantages we had sought. Here's the same thing again, but maybe more normalized. So in this example, a user document has got his username, the document has an ID, and a separate contact, and maybe also access document, contains the contact and access control details that we've factored out of the original model. So you can see how this might work. It's a simple enough idea. Each object in a Mongo database has an ID, and we put that ID into a separate document containing all the contact information. And also another example of it, we're doing the same thing with the access. So we've got a separate document, and the objects in that document refer to entities in another document, in the user document in this instance. When will we do this? Well, I guess the clear advantage emerging here would be duplication of data. So we have separate, more complex relationships modeled independently. And we wouldn't like the same data to be replicated in multiple places. So we get more flexibility. However, we have more queries when we're interacting with the data store. 2, maybe 3 queries to get back information on the user in this instance, rather than just 1. So we've seen this in action already. The Play Store, as we've been evolving it in the Playtime application, has been largely normalized. We have separate stores or store objects for each of the tracks, playlists, and users. But we could envisage a normalized version had we chosen to do so. One-to-many then. Let's look at that for a second. Let's imagine we've got a person, a story, and the person owns or maybe creates or is the author of stories. We do this in Mongoose via schemas. So we establish the person schema, and then we say the creator of the schema, of the story, is a person. So you see we've established person and ID here to establish the relationship. So reasonably straightforward principles then to establish these relationships. Mongo is designed really to work very seamlessly with JavaScript. So in our schemas in Mongoose, we're declaring arrays, and then we're following fairly predictable patterns in populating the objects we create, the documents we create in the stores, so that those relationships we've envisaged are efficiently captured. So we built our web application as a classic, what we call server-rendered web app. We've got views, built-in handlebars using the vision system. We deliver a web experience. Each page is assembled on the server and delivered to the client, and we're embedding our data then on the pages using our templating language. If the users are creating objects in our database, they're creating playlists or registering users, and they're filling out forms, submitting those forms, we're getting those posted in, and then we've got our standard controller mechanisms to extract the data, update our data store, do any business logic, and so on, proceed through the evolution. Should be fairly familiar now with that process. What we'd like to do now, though, is reveal another interface to our applications that is an API, that is clients that are not web-based necessarily. They could be mobile phone applications, they could be command line applications, could be other aggregators that are building on top of our service, or they could be front-end web applications that's built using front-end technology that are not hooked into our vision system or our controllers. We'll see examples of those a little bit later on. This world is best approached from the perspective of what's called the REST pattern. There are many protocols for implementing APIs. Of course, the nature of APIs and how they function predates the web even. But the stabilization of web protocols in the 90s and their better understanding of how they were being used in the early noughties led to this style of API development we call REST, which is what we'll be focusing on. It's well represented and discussed in those references there and others. And a common term we use is a RESTful API. That is an API that follows certain patterns that are common across this style of API and now accepted as more or less the standard way of building APIs on the web. So GitHub, Foursquare, OpenStreetMaps, Twitter, Slack, they all expose web APIs as well as dozens and hundreds and thousands of other services, if you like. Lots of websites for aggregating these services, so you can explore them. This is one that just is collected loads of them, and you can explore them and experiment with them, and they provide little hooks to get you started. Rapid API is another one. This one serves to aggregate the variety of APIs and simplify somewhat your interaction with them, including things like managing API keys and the like. And of course, there's the weather ones you may have seen before. Weather is a very popular API to access lots of free ones out there. And Weather API, Open Weather Map is a very common one that you may have some experience of. Lots of other ones, of course, in this area. Loads of public APIs for accessing weather data. And of course, you've seen that in the proliferation of weather apps on your phone that are using a lot of these free services. Building an API means some technical issues we've got to get to grips with, including this notion of cross-origin resource sharing. That is, we need to build into our server an ability for multiple clients to be able to access our service and maybe access services from other web services concurrently. This yields a little difficulty, which was addressed via the core standard many years ago, And we will be looking at how we will enable that in our application. More on that a bit later. Some of the REST concepts then. REST, remember, is a style. It's a way of thinking about building an API. It's not a protocol in itself. It's not really a standard as such. It's just a pattern. And when we talk REST, we talk about these concepts here. Resources, how to represent it, messages we sent, and the embodiment of stateless behavior in any API we implement. Some guiding principles then. For building an API, it's going to be client-server, so that's the very nature of the web itself. We want our API to be stateless, so that means that successive requests to the API are independent. Shouldn't be depending on carrying state or state being retained between requests. Should behave well with caches between our client and our server. There may be many layers of caching. These caches shouldn't interfere with the behavior of our application. Interface should be uniform and easily understood. We're expecting a layered type architecture to be possible. And code on demand is something that could be possible in certain contexts. These principles were laid down in the original encapsulation of REST around 2001 by a computer scientist called Fielding in a PhD thesis, and they do hold up reasonably well over the years. Client-server is the very nature of the web itself. The server is responsible for exposing or revealing the API. We have multiple clients connected. Stateless is part of HTTP. So it's how the underlying protocols we're using work by default. So we buy into that. We don't try to override it or supersede it. Cacheable is also part of the infrastructure of the web and the internet generally. So we rely on inherently implemented cache features, which are quite complex, rather than attempting to fight against them. Uniform interface. Well, we're looking at common ways of identifying resources, and we'll see in a moment how that looks. Largely, we're using the web URL as our identifying mechanism. And then this idea of layers. We can build systems in exposing APIs that may themselves aggregate other APIs, building layers of interesting applications. We may be executing application on the client. We're probably not going to get into that, but it is an aspect of some REST type implementations. REST then, if we're trying to get a handle on it, is basically leaning into the HTTP URI and the way web standards already work, rather than using the web and tunneling through it with different concepts and implementations. To tunnel through the web to establish end-to-end connections that are stateful has been and can be done, and there are still echoes of that available today in standards like WebSockets, widely used, and WebRTC. But APIs don't take that approach. They take the approach of building fairly standard HTTP requests and responses that follow the web rules. And that has served APIs built in that style very well over the years. So what would it look like to build an API? Well, 5 simple things to do. Give everything an ID, link things together, always use the standard HTTP methods, allow for multiple representations, and communicate statelessly. Looking at each of these just for a few moments. The solution to giving everything an ID is to buy into HTTP references. That is, to use the URLs and use the articulated nature of URLs to give meaning to those references. So for some service I might be identifying the service, identifying the category of things I'm interested in. And then here I seem to be looking via a date for a specific maybe customer. That could have been our order, maybe that's registered on that given day. Or here I'm examining the products database for a product ID. In other words, it's readable. It's not a simple GUID. We may be using GUID or these IDs we've been using as part of URL, but we're also using these segments to give us some notion of a namespace, if you like, within the problem we're tackling. Link things together. Well, as we interact with an API, we accept IDs or references, as we've just discussed, as part of the data we may be exchanging. So we're passing links, perhaps embedded within objects, to other objects. And those links take the form of standard URLs. Use standard HTTP methods. So we already have, and we should be used to, get and post. We already use get to retrieve information or retrieve complete web pages. And we use post in forms. So we're submitting form details using the post HTTP verb to deliver data to an application or service. But there are other verbs also available to us. We've got put and we've got delete. We don't really use those in forms that much, but they are part of the protocol and they're used by many web servers for other purposes. We use them in the context of REST to update specific resources or delete specific resources in the context of the API we are composing. We see examples of that very shortly. Allow for multiple representations. Well, when REST was initially conceived, we were largely dominated at that stage by an XML sort of worldview. So XML may be the chosen medium. However, since then, really, JSON has become the king, really, or queen. And we're usually going to be assuming JSON as the data format for any interchange with our API we're performing. But REST keeps that open and keeps open other options as well. Communicate statelessly. Well, this is critical, really. We would like each message we send to an API, each request and responses, to be independent of any previous requests. So if we're interacting with an order system here, we don't care if between one HTTP request or one API request and the next, the entire system has been shut down, updated, replaced, started up again. Maybe that's done in a few seconds. Or we're being redirected to another service elsewhere. Doesn't matter. Each of our requests to our API should be independent. I shouldn't be revealed, or I shouldn't be interested in the implementation details of the service as a client. So these four things then: identify resources, getting a format, meta semantics, and response codes. Well, these are all at the heart of building web-based APIs. And these are how we'll implement exposing an API in our Playtime application. We're using the HTTP get, post, put, post, delete, and there are others, but these are the main ones. And if we apply one of those verbs to any one of these URLs here, the meaning varies. So for, say, /customers, that's the URL I'm accessing. Get should get me a list of all customers. Post to that same URL should create a customer. Delete might be unused, or delete might delete all customers, which would be a bit dangerous, but you can see the idea. If the URL I'm accessing is just customer stroke some ID, then get will recover one customer's information. Put, providing some data, will update that. Post, we're saying, has no effect. And delete means we will delete that customer. And if you look then at this one, perhaps the most revealing, if we get on a URL that is customer/number/orders, we're getting all the orders for that customer. If we do a put on that URL, it doesn't make any sense. But if we do a post, well, post means we will be adding a new order. It's adding an order to the customer with that ID. Delete could be interpreted as cancelling all orders. We could make that decision. So you can see here the possible pattern that we might start to adapt as we're building an API. URLs are used heavily. They may contain embedded random IDs to identify specific resources. They're mapping a kind of a problem or namespace, if you like, users and customers in this instance. And get, put, post, delete are the options we have to change that world, to create new orders, update orders, create new customers, delete them, and in general to navigate the semantics of the problem space we're trying to implement. Somebody used to using REST, that is a developer who is used to accessing API services, understands this type of structure and can fairly quickly get to grips with how the API works by following these kinds of rules, regardless of the type of API under development. So we'll try to implement then some of this in the application we're developing. How do we go about building an API? That is, how do we expose some of the services that our application currently implements? Let's take a look at the application structure for a moment. The left here is just a snapshot of the workspace. On the right, though, is something kind of interesting. This is a structural picture of our application. Specifically, we're showing selected source files, and these arrows here represent the imports or dependencies that those source modules are relying upon. So we're seeing kind of a dependency graph. It's an acyclic graph, which means there are no loopbacks on it. Talk later on about how that's drawn. Our application then, we've got our views in this views folder with layout, partials, and the views themselves. We've got our controllers in a controller folder. And of course, we've got our models. And we're segmenting our models into different types, and we're substituting them in as needed. You'll remember that by way we've coded db.js means that we can switch between Mongo, memory, or JSON. Maybe we're using the Mongo for our main production, but maybe for test purposes, we might be using the memory model occasionally. This is the complete picture from the structural analysis I mentioned. So our application is becoming interesting now. Again, we can see the kind of architecture at a high level by looking at just the different clusters here. We can see that our main application really and the controllers are centered around here. We can see our tests over here. And then we can see our DB and our memory model, if you like, is here. Sort of three structural zones in the application. This is our web routes. So if we were looking at application from scratch, we might first have a look in here to see that we get an understanding of the application architecture. The controllers then, of course, are leveraged from here. That is, any route arriving in, we're going to be invoking the appropriate controller method from that point. And we've got a set of tests. So the tests we've built so far will exercise playlist, track, and model, and they're going to be oriented towards whatever model we select. So we have the initialization in each of these tests to pick a Mongo or Mem or JSON. These tests are giving us some confidence now that we've got a fairly robust implementation. Probably still a bit more work to do on those tests, but we've got the basics here now. We're testing for the happy path and also some failure paths in each of those test suites. So we're comfortable enough that if there are going to be bugs in our system, they're unlikely to be now in our models, or at least if we'd completed the tests, but our models are more robust. And any source of failure now is going to be possibly be elsewhere, which is a good place to be in as we introduce some new facilities. One last quick look at our project structure. Controllers and models we kind of think of as our back end. Our front end is the views. They're still really at the back end, as you know. They're server rendered. Main and roots is in server and webroots.js. And then we've got our test infrastructure, our code quality infrastructure, and our project dependencies. This code quality is based on ESLint and Prettier. And these have the rules that our IDE and indeed our build system is going to be adhering to, following the Airbnb code style guides. So how do we bring in an API into this? Well, we're going to start here with the project structure and bring in a new folder. That new folder there will be a new controller, if you like, that is going to be giving us roots and controllers associated with the API itself. So we're going to bring in a user API.js. We're also going to bring in a separate roots file just servicing the API. That's all we need in the source of the application. We're also going to, though, refactor our tests to bring in a new set of tests that are exercising the API. Remember, our tests at the moment are just focusing directly on the models. We're going to move those tests that we've already built down one level into a models package, and we're going to start populating an API package here, folder, with some new stuff that's going to exercise the API as we're going to develop it. How do we build this API then? Well, starting point will be in our server. We're going to be defining, as we've mentioned, these new roots, and the roots here will be imported, and we'll have a second invocation of server.root. So we are already bringing in the web roots we've looked at, and now we've got these API roots, which are down here. And for the moment, we'll just try out one, get. This looks very like the roots we might write for servicing a standard web type controller. All we've got is the method, the path, and then a reference to a controller. But a controller this time is an API controller, not what we might call a standard controller that is serving up web pages. This is serving up pure JSON data. When we're working with the building an API, we do follow conventions around error handling and error reporting that rely on HTTP errors. So we're not going to be, for the moment, using Joy, although we'll see how we might use that later on. But we're going to be using reporting back errors as HTTP error codes. Boom is a developer-friendly way of generating HTTP errors, and we'll install that in our application and start using it in our API controllers. So here's the first API implementation. This is going to service the get method, and it's going to retrieve all users from the database. So when a user invokes this method, and we can invoke it directly from the command line if we want. So we can just type this in here, and we should be getting back all users if there are any users in the database. So this is the implementation. Looks very much like a standard controller we've implemented before. We have authentication turned off for the moment. We'll be revisiting that. This is our handler, and all we're doing in the handler really is invoking store get all users and returning those users. So what's different here from what you're used to is that we are not generating a view. We're not invoking the vision subsystem to assemble a page out of our templates. All we're doing is returning JSON data. This is going to be packaged up properly into HTTP response, and that response we've just seen will be available in the browser if you want, but presumably it'll be a client application of some kind that's absorbing that response code, making the request. We're also generating an error here. So we're using exceptions. So if an error occurs, and that error could occur in somewhere in the database system, then we will catch the error here and turn it into a standard HTTP error, server unavailable. That's one of the codes in the HTTP standard. And we're passing an extra explanatory string in this instance. So this gives us our first look at an API implementation. If anything, it's slightly simpler than working with the web-based controllers, because we're not building more complicated view objects, as we've been calling them, that are then traversed by the templates. We're just responding to a data request effectively. So we get that back if we try it out. Let's try another one. In this case, we're going to be creating a user. And this one now is what we would have in the past been doing for a form that is handling a post request, except this time we're handling a request that's coming directly from some client, not web-based. However, the mechanism is exactly the same. So how do we implement that? Well, the implementation is a little bit more involved, but not much. We're creating a new user. So in here, we are creating the user, which is fine. If we got a non-null value back, we're happy enough. We've created the user, and here's an example of us returning the user plus a 201 code. That is a HTTP code that indicates created. It's part of how the patterns that REST expects. 201 is a HTTP error code indicating that you've posted something and it was successful and it created something new in whatever resource you're attaching to. We've two possible errors we're picking up here. We have error creating user, which could occur with an exception inside the db.userstore creation error. We also have another error handler here, database error, which could happen if the entire database is unavailable. So both of these then yield our possible error responses. How do we test these? How do we test a post? Well, we can't use a standard browser because the browser can make GET requests from the address bar, but you can't do POST requests that easily. And there's a whole family of tools for experimenting with APIs have grown up. One of them is Postman. Postman is kind of a standard in this area, and you might be doing this in the lab. It's easy enough to do a Postman GET request. You specify the URI you want to access, and when you press the button here, you're going to get a response here. You can also use Postman to make POST requests, hence the name. In this case, you would be selecting POST here. We're using the same URI, but we would be filling in the data for creating the user in this instance. And we would be expecting then that when we press the send button, we would get a successful result, and we would see the user created and visible down here as one of the responses. So that gets us up and running with the very basics. We have our existing project. We're not going to build a new project. We're going to introduce new routes to that project, make sure those routes are configured and available. And then those routes will be serviced by new controllers, and those controllers will be using our DB objects. That is, they'll be interacting with our services. And in our case, where first two examples are simply returning all users or creating a user. Now, we've already built some test infrastructure. We've been able to test our models directly. We should now really turn our attention to how can we test our API. Postman is perfectly fine for getting up and running, for seeing does the basic infrastructure of the API work at all. So it gets us off the ground. But Postman isn't really very suitable for automating our tests. It's designed as a web application, really, that you're just pressing buttons on and filling out forms. Now, you can save the requests, and you can have a suite of requests in a kind of a type of playlist as it happens. But it's better for us now to move on and use our test infrastructure we've already built to build API tests using the unit testing or test suite mechanisms we've already looked at. This, of course, is the world of automation. If we can automate, it means we can run it continually. It means we can perhaps have it triggered automatically in a pipeline. Maybe the tests are run for every check-in, or maybe for every merge onto master, or via some QA procedure. We already have Mocha and Chai in our project. The infrastructure is already there, so we're just leveraging that, really. And as we mentioned earlier, we're building a new suite of tests now, and these new suite of tests are coming in here to exercise the API. To access an API, we'll use Axios. This is a very popular HTTP client library used in client-side applications on the web as a kind of a standard option. We'll also use it here in our tests, so that when we're exercising our API, we're going through the standard HTTP protocol. It's probably worth learning a little bit more about this library. It's very widely used, fairly straightforward to get to grips with, and it's got some good documentation to get started with. Let's see how we use it. We're going to build a new interface, or gateway, we'll call it, playtime service. This will be an object with methods that encapsulate access to the API, so our tests can be kept at a fairly high level. So we're not going to use Axios in our tests. We're going to use functions we're writing here, like create user. And create user then will use the Axios function directly. So here our create user is calling Axios post. This is the URI, and this is the user you want to create. It's an async method, so when it responds asynchronously, we'll dig out the data and we'll return the data as the value of this function. So we're keeping it up at a fairly high level. This test will be initially pointed at localhost. So it's a new fixture we're putting in there, and we're importing the fixture here into service URL. So we're using service URL there. Here, playtime URL we're calling it. Okay, that's our playtime service. We can start to build a test then that uses that service. So what do these tests look like? Well, here's the first one. It's going to be structured very similarly to our tests for the models we've already done. I'm going to have a setup and a teardown. We're leaving them blank here for the moment, but just putting them in as placeholders. And here is how our first test looks like. We're going to use the playtime gateway to create a user. It's Maggie, and we're awaiting a response. We are expecting to get back a user that contains all the fields provided in Maggie, maybe more. So we're using the assert subset we've spoken about. And we're additionally saying I would like an ID to be present. So we've an extra is defined new user.id. The ID isn't null. So that's our first test, and you can see the idea of how we might evolve these. They look quite similar in many ways to the model test we've built. But remember, we're testing not only the basic features of the model, but also the whole infrastructure of the HTTP connection, and later on the HTTP error codes if there are going to be error codes. So our tests now are getting closer to being what we may call end-to-end tests. They're testing core features, but also the entire infrastructure around exposing and servicing an API that's part of our application. This means we can keep going now and start to build tests exercising these endpoints. We're trying to make them consistent, methodical, trying to test for multiple types of test cases. And remember, these tests correspond approximately to what you might remember from relational databases. Get, put, post, delete kind of suggest select, insert, update, and delete SQL statements. So the semantics of these types of verbs we're using the HTTP standard have some alignment here. But of course, we've got IDs and further paths associated with the requests we're making. So if we call get on status, we're getting whatever status is. If we supply an ID, we're getting a status with an ID of 3. Post means we're creating some new status. Put means we're editing. And delete means we're possibly deleting something with an ID of 4 in that instance. These are the semantics, as we say, of our interpretation of get, put, post, delete in REST world, and how we start to think about what we should be doing as we're using those verbs in our application. I mentioned response codes and how we expect, how we're going to use the Boom library. These are the codes that are part of HTTP standard, and they're the range of codes we typically use when we're building APIs to adhere to roughly what web applications and web browsers would be displaying or handling. Also, these would be associated with caching responses and the like. So we're saying 200, 201, 204, 400, 401, 404, 405, and 500. Boom allows us to create all of these errors just by using these phrases. And we've seen 1 or 2 examples of that already. So here's now a more complete picture of the endpoints around users: get, post, delete. And we can see we're getting all users. We're creating one user. We're sticking in possibly something that's a bit dangerous. Maybe we'll take this out later. Deleting all users. And then we're doing also a get of one specific user. So we've had to write then or extend the API controller we've been building with these 4 methods. And this is the implementation here of these. So we've got our find one, create, and delete all. Some of the error codes you can see here. Delete all, for instance, returns a 204. We look at what that means. No content. So this is a convention for when you do a delete, is you pass back a 204. So we're doing that there. A 201 is what we're passing here. This is for the create. According to our table, what does 201 mean? Resource created. So that's what the interpretation of the HTTP code semantics. We need to extend our playtime service to give us a bit more features in our gateways, we're calling it. So we've got create user, and we've also adding in get user, get all users, delete all users. So this is just a little wrapper around Axios. We don't really need this necessarily, this object, but we're using it because it simplifies our tests, which can start to look a little bit more readable now because they're up at a slightly higher level. So we're testing post, testing delete, testing get. And you'll see the general structure of these tests is not a dramatic departure from the ones we've already built. We're creating a set of test users in our setup. Not doing anything in our teardown for the moment. Then we're testing basic creating user, testing delete all users, and testing getting one user by ID. And these tests get us up and running with the basics of the application. Returning to our overall picture, we now kind of have two subsystems on the go here. This is our application proper, if you like, and the dependencies therein. This is the application and all of the sources, leaving out the tests for the moment. So we're seeing here, this is our entire application now. It's becoming more interesting. We've got our API routes. We've got our web routes. And we see the dependencies in our schemas and on our complete database implementation. The tests are doing their own thing, and they're starting to evolve. We've got playtime service, test utils. Playtime service is used by the API tests, and the playlist model, user model, etc. are all relying directly on the fixtures and test utils. These diagrams are structural diagrams. They're generated using this tool here. This is a Watford originated company, Structure 101. You can go and download the application and point it at your project to generate this type of diagram and many more. I might do a little lab on how you would do that a bit later on. Very useful for visualizing large applications. Okay, that gets us up and running with a basic API, users, and then starting to evolve tests for that basic API. So you'll get a chance now to tease out your understanding of this in the labs by looking at playlist and perhaps tracks and start to roll out APIs for those. Remember, the purpose of building an API is to make our application available to other types of client. These could be non-web clients, that is, they could be applications for mobile most typically. They could be other applications, other server-based applications, if your service perhaps is being syndicated in some way. Or they could be web clients that are not based on server-render technology, that is using front-end frameworks who access our core services via an API. And we'll be looking particularly at that in future classes.